Good, then welcome back. In today's lecture, the penultimate lecture for this course, we're going to discuss what happens when you combine Goldstone's theorem with, which pertains to symmetry breaking, with local gauge invariance. Spontaneous symmetry breaking with local gauge invariance. This is the question, and the answer to this question resolves a puzzle to do with local gauge invariance. So if you consider a gauge theory, say SU2 gauge theory, then there's a puzzle, and the puzzle is the following. The gauge bosons, the ones that are these auxiliary bosons that are introduced to give this theory this local gauge symmetry, they do not have an explicit mass term. So there's no way to have a massive term. You might want to say, okay, suppose we have some gauge bosons and suppose they're massive, then we might want to add some kind of mass term which could only look like this, right? And so this is, why would you like to do that? Because these particles exist in nature. It turns out that in the weak theory of interaction, in the theory of weak interactions, there are massive gauge bosons. So we see them, so we better be able to model them. But if you do this, if you naively put a mass term here in the Lagrangian, then this actually breaks gauge invariance. And the reason that it breaks gauge invariance is that under a gauge transformation, these gauge fields transform to themselves plus some derivative terms. And this just doesn't transform in the right way. So that's the puzzle. We have a local gauge invariant theory. We want to have some mass terms, but we can't. And it turns out the resolution to this puzzle is via this Higgs mechanism here. So again, whenever we have a puzzle in physics, it usually points to there being additional degrees of freedom which can relieve the tension. So there's this tension here, right? Local gauge invariance and a mass term here. And these two things fight each other. They don't like each other. The mass term here is not locally gauge invariant. So local gauge invariance fights this mass term here. So you have this constraint that you can't resolve. But whenever you have constraints in physics, constraints in physics can be solved by adding new degrees of freedom, and not just physics, in maths, right? So if you have n equations and m unknowns, and n is bigger than m, then you're not going to expect a solution. So and in the case where you have lots of equations and very few unknowns, this is over-constrained. There's typically no solutions. And a naive way, a really naive way to get over that problem is to just add unknowns until you have enough equations that they equal the number of unknowns, and then you have a solution. So this is, it sounds very naive, but this is precisely what we're doing here with this Higgs mechanism here. We have this demand, this constraint here, this one here, they're incompatible with each other. And we're going to try and resolve these incompatible constraints or demands by introducing new degrees of freedom. And the amazing thing, right, why physics is so exciting is every new degree of freedom in high energy theory, that's a particle. So when you do this, you're making a prediction. And when you make a prediction, you can test the prediction. And if you're right, then you win a Nobel Prize. So there's a good reason, purely financial reason, why you might want to try and solve constrained problems in physics. Of course, there's other reasons, like we want to understand and explain the universe. But at the purely financial level, there's a good reason to want to solve this problem. The alternative, like if you do postulate new degrees of freedom and you do not find them, so you reject the hypothesis that there are new degrees of freedom, that is also, you learn something in the process as well, right? Maybe you don't learn as much. So as you might be aware, this supersymmetry is around that solves a constraint in high energy theory by adding in new degrees of freedom. We postulate that they're there. And we've rejected the existence of these supersymmetric particles, at least for certain energy windows now, by the LHC. Okay, does that mean they're not there? Not at all, they could still be there. But what we're learning is that their explanatory power is shifting and changing as we get new and new bounds on the existence of these new degrees of freedom that were postulated many years ago. All right, so what we're going to do is we're going to, like before, we'll go through a kind of toy model to get a feeling for what happens when you combine spontaneous symmetry breaking with local gauge invariance. And then we'll take a look at a much more serious example in the sequel. All right, so this is called the Higgs mechanism, what I'm going to describe to you today. And the toy model, well, it's not that toy, it's a pretty serious model, is the abelian case. If you like, this is a toy model. This is not the Higgs mechanism as it happens in the standard model. But this is a sufficiently intricate and difficult to solve model that it has applications all throughout physics. Now, what's the content of this theory? So this is a theory of a complex scalar field which, if you like, is just a doublet of scalar fields. No real harm in thinking about it like that. You could do that if you wanted to. But it's traditional when you have two fields, you can always stick the number I there and you build it into one complex field. So it's a theory of a complex scalar field and coupled to a U1 gauge field. So we've been through gauge theory, we know how to couple fields to gauge fields. It's a little bit different here than the cases we've considered before. We usually have, in the cases before, had fermion fields when we discuss gauge theory, but there's no harm in attaching it to a scalar field. Everything, all the derivation goes through as it did before. I'll just write out the Lagrangian. Oh, I forgot the minus sign up there. So the Lagrangian is the curvature, and we have some derivative term for this complex scalar field. If you work it out, it's just the same as if you use this doublet there. And we have some potential like this. This is some seriously non-trivial model. So firstly, we got to establish that it is a gauge theory. Let's do that now. Wow. All right, let's just check that that's all what we expect from a gauge theory. So we have this independent at every place in space-time transformation of the field. I didn't draw the X in here. We introduced this gauge field A mu to compensate for this freedom that we have everywhere to redefine the field by this scalar, complex scalar that lives of norm 1, so it's just a phase. And in order that the whole theory is invariant under this transformation here, we have to allow that this connection field transforms like that under a gauge transformation. Now we've already seen the argument for why this thing is invariant under this transformation here. If you realize that this number here is just a phase, it's an element of the circle in the complex plane of unit length, then it's easy to see that this term here is invariant under that transformation. The covariant derivative is invariant, and phi being redefined by that is invariant. And similarly, if you design the potential correctly, that'll also be invariant under local gauge transformations. And so what kind of potentials are we going to allow? Well, we have in mind exactly the same potential that we've used through all our spontaneous symmetry breaking examples. Namely this one here. So we could have put more complicated potentials, but this is the one we used. So that's our theory. We have this theory here. It's a very non-trivial interacting theory. Phi interacts with A mu. I call it via this term here. And V of phi is quartic, so we're not going to be able to expect to exactly solve this model. There's no hope of that. So, the way we're going to analyze this theory is precisely the same way as we've analyzed spontaneous symmetry breaking in the previous lecture. We're going to find a classical configuration which minimizes the Hamiltonian for this theory. And then we're going to expand around that classical solution and look at the small deviation dynamics around the classical solution. And that's where things get really, really very interesting indeed. So because the steps they're the same as before, I'm going to skip one or two of those steps. Okay, I hope that's not sort of surprising. You've seen this thing appear a couple of times when we looked at spontaneous symmetry breaking. This is the one of the minimizers here. There's two, right? Plus and minus. In fact, there's a whole family of them multiplied by a phase. But we're just going to take this one. You know, we're free to add in any kind of phase that we like, and it will still minimize the potential. So there's this circle of potential minima. I mean, so far, so nothing, right? I've just shown you that there's this classical solution to the equations of motion that corresponds to the classical minima of these nonlinear differential equations. So this is all classical still. I haven't done anything quantum yet. Just classical field theory. And then the next step is the really interesting one. We're going to expand L around phi equals phi naught. And we're going to study what's going to happen to a small fluctuation around this steady state solution to these equations of motion. So let's do precisely that. There's our classical solution, and we've got some fluctuations here. There they are. So phi 1 and phi 2 are just the deviations in the real and imaginary directions for this scalar field. And in terms of these new degrees of freedom here, these are the new fluctuating degrees of freedom. That's the classical solution. Then we can expand this potential, just substitute the solution here, and keep things to low order in these phi's. So these are meant to be small. So then when you retain things only to order, say, phi cubed or something, then the potential has a very simple form. This is an exercise. Oh, that was a bit silly. There's a lambda somewhere in all of this story, isn't there? Yeah, okay. That lambda has nothing to do with that lambda up there. Let's just mu, alpha, beta, gamma. Gamma's not safe either. Small phi is also not safe. Oh, var phi. There you go. Yeah, that one's safe. Haven't used that one recently. And it turns out when you expand around the classical minima, the potential, it has this particular form here. In particular, there's no imaginary part. That cancels out. That's not surprising, actually. You wouldn't expect to see the imaginary part at order 1 because the potential is real and is part of an absolute value. So around phi naught, our Lagrangian becomes, well, the stuff before, the F stuff, and then we get the interesting stuff right here. So we get this phi 1 on root 2, oh sorry, 1 on 2, d phi 1 squared. So we get some phi 1 stuff, very interesting. We get some phi 0 stuff, sorry, phi 2 stuff. Okay, so far so nothing. And then what else do we have? We have the potential, so we have to subtract this off. So and that's where we learn we start to learn interesting stuff right here. So firstly, we confirm what we already knew, right? Namely, that we're going to have one massive boson and one massless boson by Goldstone's theorem. And which one is the massless and which one is the massive? Well, you just look at this equation here. That's a constant, so it's gone. And we see that this particular fluctuation, the real fluctuation, has a mass. There's an effective mass now for this fluctuation, given with mass mu squared. And this guy here is massless, effectively massless. Okay, so far so familiar, right? We haven't done anything about the actual covariant derivative term there. I have to expand that now because that's what couples phi to the gauge field. So there's dot, dot, dot. I should have written that. There's more terms, which I haven't yet done. But at this stage, we can already identify an effective mass for phi 1. Okay, I should have written this not as D, capital D's, but as partials. Because we've got to expand those D's correctly. Those big D's. So what about the kinetic energy? Let's expand this thing here now. Let's do it properly. So, well, as predicted by this thing here, we're going to get d mu phi 1 squared plus a half d mu phi 2 squared. So this is good old-fashioned kinetic energy for these fluctuations. And then we're going to get the interesting stuff. E phi naught a mu d mu phi 2. Okay, it's a new looking term. And the really interesting term comes next. That term is the one that should pop out when you look at it. So E is a constant, it's like 1 on 137 or something. And phi naught is a constant, right? It comes from minimizing this potential. And that thing there, well, that looks like the mass term that we wanted to have from the outset. So this expanding about the minima and looking at the effective dynamics near the minima shows us that these originally massless gauge bosons behave for all practical purposes as though they have a mass, depending on how big phi naught is. And the whole Lagrangian is still gauge invariant. I haven't broken gauge invariance in any of these steps here. There are further terms here. They're small nonlinear corrections. So, but the lowest order stuff to this Lagrangian looks like a free massive phi 1, a free massless phi 2, and massive bosons A mu. Not bad, huh? So that's all classical. Now for large fluctuations, when this approximation is no longer valid, if you imagine your field is allowed to fluctuate on huge energy scales, then the interpretation of all of these terms goes away. You can no longer Taylor expand and say that some terms are small. So this term here is only small when these are small fluctuations for very low energies. For very large energies, this theory again is you can't really say that it has massless bosons or massive bosons any more than you can say anything else. So it's only at the perturbative low energy limit does this work. So this is a classical result because I didn't do anything quantum yet, and it's a low energy result. So it only works when you consider small fluctuations about that classical solution. Now that's as long as you can find a way to justify that, then that's fine, right? I don't think that any of these steps are particularly controversial. Now I'll just say one or two words about the quantum version. So we've done all this stuff at the classical level, but it's worth sort of pondering, does this hold in any sense in the quantum level? Now the analysis is much more involved, unfortunately, for the quantum case. But I'll sort of walk you through what you would want to check. Well, firstly, step one is to use path integral quantization on this Lagrange density L. I think that's the easiest way to approach this problem, although you could do a Hamiltonian version on the lattice if you wanted. There's no, but I should, or even a lattice version in Euclidean lattice. But I'll warn you that lattice is not particularly well suited for this problem, at least as it's written, because the lattice is more a kind of, well, no, I guess this would work fine on the lattice as well. Yeah. So you use a path integral. We're going to use the path integral quantization on L, and so we regard So we're going to have to do path integral quantization. It's not enough just to stick it in the path integral. We've got to generate it. We're going to use the path integral as a box to generate Feynman diagrams. Otherwise, it doesn't make the path integral doesn't necessarily make any sense. So to do that, we're going to need to identify a free part that's easy, and that's given by this stuff here. So this is the minus mu squared phi 1 squared. It's the effective massive phi 1 field. We have the massless phi 2 field. There's no mass there. That's the massless gauge boson guaranteed by Goldstone's theorem. And what else do we have at order 1? Well, if we look here when we expanded, we've got the, of course, the dynamics of the gauge field itself. There they are. When we stick it in the path integral, we'll have to do this Faddeev Popov thing, but that's all L0 Lagrangian stuff. And what else are we missing here? Not much, right? We've expanded the potential and included all those terms in there. That's good. We've dropped off that constant when we expanded the potential, a shifted constant. constant is nothing, doesn't do anything to the dynamics. And we have one more term that we're going to regard as a 0th order term, and it's this one here. We're going to think of that as a 0th order term. Yeah. So that's L naught, and L int is the rest. And we regard that as a perturbation. And it consists of a bunch of terms. There's, what sort of things are in L int? Well, this guy here, for example, is an L int. So you think of this as an interaction between the gauge field and the phi 2 field. What else is in L int? Well, that's pretty much it. That's the is the U1 gauge. Oh, yeah. And the higher order terms here, of course, are in L int. They haven't gone away. We're going to include them just here in L int. So there's cubic terms and there's quartic terms. And all of these terms lead to vertices in the Feynman diagram. So you do this perturbation theory, you expand the exponential, you look at the Taylor series, you notice patterns, and you quantify them in terms of Feynman rules. And all of these things in L int will turn into different kinds of vertices in the Feynman rules. I'm not going to enumerate them all, I'll just focus on one that's kind of interesting for the fate of the mass of these bosons. So this term here that I circled, yeah, see that term I circled up there, the coupling between the gauge field and this phi 2 field. That's a vertex in this perturbation theory. So I'm going to draw that vertex. So in momentum space, perturbation theory, that's what this vertex looked like. Momentum space Feynman rules. So that's what happens. So now let's look where's the mass at the quantum level? So as you do computations, you have to ask yourself, what is the mass of this A mu particle? Where would you find it? So it's got to be an operationally well-defined quantity. It's got to be something that you can observe in an experiment. And the place where you find masses in field theory for for particle fields like A, mu, phi, psi, are as poles in green functions. That actually belongs to L int. Sorry, I should have put it. I put it in the wrong part of the Lagrangian. So that also leads to a vertex in the Feynman rules. It leads to a vertex of the form dot. We'll see it come up here. And so as you sum up diagrams, that's the first order contribution for a boson to boson transition amplitude. And here we get a second order contribution where the gauge boson turns into this phi 2 particle, and then it turns back into a gauge boson. So it flips from being a gauge boson back into a phi 2 particle and back into a gauge boson. And there's lots and lots of higher order terms with loops and all kinds of other horrible things. And if you evaluate these terms here, and you find, mu, right? There's a chance for it to go from being a mu boson to a nu boson. When you evaluate these Feynman rules, we end up with that expression there. And if you look at this particular term here in the diagram, and all the other terms will have this feature as well, what it looks like is that this gauge boson, well, it turns into this phi 2 and then comes back to being a gauge boson. But it turns out you can eliminate this phi 2 from all the Feynman diagrams. Right, that was the abelian toy example. This was really not so trivial. And to do proper calculations, there are many, many more diagrams that you have to sum up, which I have not even begun to write down here. But the mechanisms, these are the mechanisms that are at play. Okay, now that we've done an abelian case, let's do a non-abelian case. Perhaps something goes wrong in the non-abelian case, perhaps something changes. Well, it doesn't, but there are subtleties. There are additional things that take place in the non-abelian case. So non-abelian gauge theory. I've written it down pretty generally here. So, well, why not? We'll do the general theory, and then we'll specialize to the case of U1 cross SU2, which is this the theory of weak interactions, which we'll end this course on. So we're going to look at a general gauge group G. So way more general than SU2. We're going to look at like SU whatever, or SP or SL, or some completely general gauge group now. So we didn't really do gauge theory at the level of a general continuous group, but it's very, very similar, and in the end when we apply it, we will apply it just to SU2 cross U1. But we'll just write it slightly more generally like this, and I'll try and point out the steps which are generalizations of what we've done already. So if something transforms according to a continuous group, it means that you take this vector here and just multiply it by a representation of the group, which is a matrix. So here we're doing a couple of things. So if little g is an element of our group, then little g is going to be of the form of the exponential of some parameters e alpha a t a, and these span the Lie algebra of this group. This is something we've seen several times throughout quantum field theory, that you can always express an element of a group as the exponential of the Lie algebra, or something in the Lie algebra of the group. And these are matrices, and depending on the representation, they may be bigger or smaller matrices. And for the cases we've been considering throughout this course, we've really only had one group of interest, and that's been SU2. And SU2, the Lie algebra is three-dimensional, and one representation that we've used throughout is that these TAs are the Pauli matrices. In the 2 lectures ago, I showed you how to build other representations of SU2 in terms of bigger matrices. They still behave just like SU2, but they're just bigger. That's another example of a representation of a continuous Lie group. And here I'm just leaving it fully sort of unspecified, so you can stick in the generators that you like and the Lie group that you like. All right, so far what have we got? We've got some scalar fields, and they transform under a global symmetry, which is a continuous group. Just to pi of g, just to stress it's a representation of the group, is really pedantic, right? But it's, you have the group as this abstract thing, and then you have a representation of this group as a bunch of matrices, and it's worth stressing that's pi of g just tells you, I'm working with matrices instead of the abstract things. We'll just write, just to make our notation a bit smaller, we'll just absorb that imaginary number I into the matrix TA. Okay, we're going to build a gauge theory. So we're going to promote it to a local symmetry, meaning that we're going to do an independent such transformation everywhere in space-time. everywhere in space-time, we're allowed to do a separate, independent, different one of these transformations. And in order to get derivatives, we replace the, you get derivatives in the sense of a gauge invariant Lagrangian involving derivatives. We replace d mu by, well, the covariant derivative. So the beauty with doing these kind of derivations is that after a while the steps become so repetitive that you can't help but remember them. And then as a consequence we get this gauge field A mu being introduced at this stage. There we go. Great. So that's when we introduce this gauge field here, what this does, right, is compensate for this extra symmetry here and allow us to build non-trivial Lagrangians which transform under that transformation everywhere independently in space-time. So now we can build a kinetic energy term. And it's unfortunately going to be a bit lengthy because it's going to involve phi, and it's going to involve t's and a's and so on.
One question.
Yep.
Is it really on the right side? Is it really d mu phi? Or is it only d mu?
It's d mu. Oh goodness me! Yeah, that's really bad, isn't it? Thank you. The question was, is that d mu phi? No way. No, that would make it some crazy weird thing. Yeah. All right. Yeah, that was bad. So if we use this to define a kinetic energy term, as before, like to try and build a nice non-trivial Lagrangian, then we're going to, well, have to square it. And that's what you get when you square the kinetic energy. Lots of indices and all kinds of stuff happening, but we can sort of break it down into something a bit more smaller concrete steps. So we've taken d mu phi squared. So that's going to be and then we're going to have to use the fact that this is a matrix, right? JK, and that's a vector. And then we're going to square that whole expression. So then we'll just sort of go through step by step and compare the terms from this square thing down here with those up there, and there's a half there as well. All right, let's check if we can understand at least this first term here in the kinetic energy. Well, we get a d mu phi k, but remember d mu here has got an identity operator there, so it's really a delta jk. So this is d mu phi j squared times a half. So at least that term matches. And we've got this, then we've got a cross term, for example, where we've got d mu phi j, and then we've got an a mu t a g jk. Do we have that term over here? Yeah, we do. There it is there. And we get that twice, so there's no factor of a half there. And we get a final term, which is just this term squared. So no magic or mystery there. It's just expanding out the square. Now we're going to combine this with the spontaneous symmetry breaking story. suppose in our Lagrangian we had this potential V of phi. What V of phi? Well, the same one as always. Namely this one. So we add this potential on into our Lagrangian, we minimize the classical potential energy, and we find that this vector phi has some classical minima at some phi naught, some vector. And this is just the wine bottle potential. And the field here just drops down into the circle at the bottom of the wine bottle and gives us that classical minima there. And then, what's the next step, right? We've done this like 5, 6 times now, maybe 3, 4 times. We expand around phi naught. So we have some Lagrangian. We've been very vague about what the Lagrangian has in it. The Lagrangian at least has a kinetic energy term, and the Lagrangian at least has this potential energy term in it. It may have some other stuff in it, but that's the 2 bits that we need that the Lagrangian has. So we expand around phi naught means that phi, the field phi, is it's just the classical minimum, which is, we've worked out already, plus epsilon times by, well, some fluctuating field. And we're going to collect everything to order epsilon. And the crucial term will come from when we substitute that field into the kinetic energy term up there. That's when we'll learn something very interesting. So it's an exercise that when you substitute in this fluctuating into the kinetic energy, we're going to get all kinds of terms. But there's this one term in particular that's very, very interesting. So let's try and imagine where this comes from just by looking at the kinetic energy and looking at what we're expanding around here. So if we substitute in this into the kinetic energy up there, then there's only one place where there's a quadratic term involving the gauge boson, so it's the last term in the kinetic energy. And if you expand to order 1, then you get phi naught in place of phi up there, and you get phi naught in place of phi up there, and you get A there. So it looks very similar to the original Higgs model example, the abelian Higgs model example we considered at the beginning of this lecture. And indeed, that's precisely what this matrix is. This matrix here is given by those t's applied to phi naughts. So we'll just write that out. Is a J. Now this may not look like it at first sight, but we'll look at it a bit deeper. This is a positive semi-definite matrix. So that sort of be a bit carefuler, I guess. Just like in the previous lecture, I want to make it clear that A, B are the matrix elements of this matrix here. And so they run from 0 to the dimension of the group -1, these A and B. So it can be a big matrix. So for the example of SU2, and the fundamental representation, then A equals 1, 2, 3, or in that notation, 0. Wow. Let's just let the A's and B's run from 1 to the dimension of G. That makes it less annoying. So for this case here, in the fundamental rep, these A's run from 1 to 3, and T1 is I times Pauli X, T2 is I times Pauli Y, and T3 is I times Pauli Z. Let's try and build this matrix here. And so what does phi have to be? So to be compatible with this representation here, this vector phi has to be 2-dimensional, because you can't multiply a 3-dimensional vector by a 2-dimensional matrix. So see here, T is applied to that vector there. So T is a 2-by-2 matrix in this case. So in order for this to work out, phi is just a 2-dimensional matrix like that, a 2-dimensional vector like that. And for the cases we usually consider, phi naught looks something like this. So we can now build this matrix here and have a look at what it looks like. A little bit of linear algebra. So we need to work out what is T1 of phi naught as a vector. Well, that is I, 0, 1. T2 phi naught as a vector is minus, no, not minus, I, minus 1, yep, minus 0, 1, like this. And the last one that we'll need is T3 of phi naught, and that will be 1, 0, like that, all times by I. And now we have to build this final thing here, which we get by taking the inner product of this vector with itself plus the inner product of this vector with itself plus the inner product of this vector with itself, depending on what A and B equals. So let's start building out that matrix. M squared, let's look at the 1, 1 entry, for example. So the 1, 1 entry is this vector times by itself. I'm missing a minus sign, I think. Oh no, it's in the Lagrangian, so the minus sign is good. So you can see I'm going to get a minus here when I consider A and B as 1, and I compute this sum over the entries of the vector here, j equals 1, j equals 2, we're going to get a minus sign. So that's like, oh. So, so this is minus, it's minus by a positive semi-definite matrix, this thing here. So when we compute the 2, 2 entry, we just compute this thing twice. We always get g squared out the front or the back. And here we get minus 1 again. Oops. And then let's work out the other entries of this matrix. So now what about 1, 2, this entry here? So what's the inner product of this with this? Well, if we look at it, we see that's minus I. What's the inner product of 1 and 3? That's 0. Get that one for free. Like this. And then look at the 2, 3 contribution. Is there one there? No, that's also 0 as well. There we go. So that's the matrix, so-called mass matrix, for this very specific example of SU2. And is it indeed negative of a positive semi-definite matrix? I sure hope so. Let's have a look. So I think so, yeah. I can't for the moment see if that's positive semi-definite or not.
What was the definition of positive semi-definite?
That if it's diagonal, that the eigenvalues are 0 or greater than 0. So is this minus 1 times by a positive semi-definite matrix? It actually doesn't look like it at the moment. Maybe I made a mistake. 0, -1. So I can't see it at the moment. I don't think it is positive semi-definite. I don't think it's minus 1 times by a positive semi-definite matrix. So I must have made a mistake somewhere in this derivation. And I don't see where.
I think it must be negative semi-definite.
Negative semi-definite. This one?
Yes. Called the -1.
This is negative. Yeah, this is good. Yeah, I agree.
And when it should be semi-definite, then all the signs should be the same. And so when we know there the -1 would make it, all the others should also be negative in this special form of matrix.
So I'm more worried about this block here.
Yeah, I tried it in my head, and I think it should be all negative.
All right, okay. So, okay, then let's make it an exercise. Is negative semi-definite? Which it should be. So I mean, I suppose you could look at the determinant, right? So it's -1, +1. So it's 0 determinant. Okay. Actually, I'm inclined to agree with you that now that it's negative semi-definite. But let's make it an exercise. Good. Now, I will make one final comment and then we'll stop for today and we'll end in the next lecture with the Glashow-Weinberg-Salam theory of weak interactions. So the final comment is to do with the choice of representation. Now, here, we didn't see it, but it can be the case that you choose a different representation here. So like I chose this fundamental representation, but that's a degree of freedom that we have when we build a theory. We didn't have to choose the fundamental representation. We could have chosen a bigger one for SU2. And if we did, then these matrices would be bigger matrices. They might be 3x3 matrices or 4x4 matrices. Now in the fundamental representation here, we saw that this state here was, it wasn't annihilated by any of these matrices here. So there's a contribution from all three operators there give a contribution. But it could be that it's annihilated. So the final comment I want to make is that so it's possible by choosing your representations, choosing in this case not the fundamental representation but say a spin 1 representation, to imagine a scenario where you definitely get 0 masses in this mass matrix. And that's important because in the theory of weak interactions we know that 2 of these bosons have a mass, but 1 has a mass, is massless. So we need, or is it the other way around? I forget actually. There's the 2 W's and the Z. The Z is, I forget. Z's massive, right? So I think there's 2 massless ones. Yeah. Yeah. So we get a massive boson, but we also get massless bosons. So you want to at least find a way to imitate that with this spontaneous symmetry breaking mechanism. Indeed, you can, as long as you find representations that leave the vacuum invariant. Then you get these 0 eigenvalues, and effectively 0 massless bosons. And so that's where I will stop today. And in the final lecture, we will discuss this, as I said, the generalization of this to fermions and this Glashow-Weinberg-Salam theory of weak interactions. Okay, thank you very much.